Our home planet is so tiny that over 1 million Earths could be contained within the Sun, a star positioned approximately 150 million kilometers from us. However, this sun represents just one of an estimated 400 billion stars traversing the Milky Way galaxy, a formation so vast that light requires around 100,000 years to traverse its entire breadth. Yet even this immense scale hardly readies you for what lies immediately past our galaxy, roughly 2.5 million light-years distant. Spanning approximately 220,000 light-years, the Andromeda Galaxy encompasses nearly 1 trillion stars, making everything we consider home seem minuscule by comparison. Currently, it is moving straight towards us. What comes next is an exploration of such immense distances that they start to alter all your brain's inherent perceptions of magnitude, separation, and our true position within the cosmos. Should you appreciate having your understanding of reality broadened by genuine scientific insights, please think about subscribing to this channel and backing this video. Let's get started. You likely believe you grasp the true size of Earth, having viewed orbital photographs depicting the planet's curved, blue skyline emerging from the dark void of space, with landmasses extending over oceans that appear to encompass half the globe. From such a vantage point, its magnitude seems self-evident. Our planet appears vast, and indeed, by the measures of daily human existence, it genuinely is. Earth is a spherical body with an approximate circumference of 40,075 kilometers at its equator and a diameter of around 12,742 kilometers. These figures are exact, having been determined via satellite monitoring, GPS technology, and hundreds of years of geodetic measurements. However, a significant distinction exists between a precise figure and one that is easily comprehensible. Our minds develop to interpret distances based on travel time by foot rather than astronomical dimensions. Therefore, instead of merely listing the measurements, envision experiencing them firsthand. A commercial aircraft, traveling at approximately 900 kilometers per hour, would require around 44 hours of continuous flight to complete one circuit of the planet along the equator. This equates to almost 2 entire days airborne without touching down, without refueling or altering its course. Should you attempt this identical journey by automobile, maintaining a constant speed of 110 kilometers on an unbelievably straight road, encircling the globe, the expedition would demand over 15 days of non-stop driving. Such is the true magnitude of the world upon which you stand. Throughout the majority of human existence, Earth seemed even vaster. Primitive humans mainly traversed on foot, covering maybe 4 or 5 kilometers hourly across expansive terrains. Expeditions that we now complete in mere hours once spanned weeks or even months. When human groups started their exodus from Africa, many tens of millennia ago, the slow dispersion that ultimately distributed our kind throughout Eurasia and into the Americas transpired over thousands of years. Whole generations journeyed across environments that surely appeared boundless. Our perception of scale developed within that context. The distances encountered by our forebears involved rivers, valleys, mountains, and plains. The human mind was attuned to horizons quantifiable in kilometers, not thousands of kilometers. Consequently, our planet seems immense to us, a genuine biological perception, yet this instinctive sensation is the initial misconception we must overcome. As we start to investigate the universe's actual dimensions, an unsettling phenomenon occurs. The instant we contrast Earth with its cosmic surroundings, our seemingly vast world starts to diminish, and it does so quite rapidly. Let's begin with a familiar concept: vertical measurement. Within the western Pacific Ocean, the Mariana Trench, a geological fissure deeply incised into the seabed, contains the deepest identified location in Earth's seas. Its deepest spot, named Challenger Deep, plunges approximately 11 kilometers below the ocean's surface. This particular depth is challenging to grasp in isolation at the trench's base. The water pressure surpasses 1,000 times the atmospheric pressure found at the surface. Temperatures remain slightly above freezing, and solar light vanishes well before reaching the lowest point. This renders the deepest parts of the ocean perpetually and entirely dark. Accessing such an environment has consistently posed immense challenges. Merely a few specialized underwater vehicles have ever ventured to the trench's base, Every single journey demands engineering robust enough to endure immense compressive forces. Such forces would instantaneously crush the majority of standard ships. From the standpoint of human exploration, the Mariana Trench appears otherworldly, but a particular figure dramatically alters this viewpoint. Completely. The Earth's diameter measures approximately 12,742 kilometers. When contrasted with the planet's overall dimensions, the ocean's deepest trench constitutes a vertical variation of just 11 kilometers. This implies that the Earth's lowest point accounts for under 0.1% of the planet's entire diameter. To help picture this disparity, envision reducing Earth's size until it matches a regular basketball, which typically measures around 24 centimeters across. On that reduced scale, the entirety of the Mariana Trench would be shallower than 0.2 of a millimeter. This measurement is less than the thickness of numerous paper sheets. Should you pass your hand over the basketball's surface, you wouldn't detect the trench whatsoever. The whole planet would seem nearly flawlessly smooth. This also applies to mountainous regions. Mount Everest, Earth's highest elevation above sea level, ascends approximately 8.8 kilometers above the adjacent landscape. In comparison to the Earth's diameter, Everest represents an astonishingly tiny characteristic on our planet, scaled to a basketball. The world's loftiest peak would stand merely about 0.17 millimeters tall. This dimension is narrower than a single grain of sand. Vast mountain chains that define continents, such as the Himalayas, the Andes, and the Rocky Mountains, would practically disappear into an almost flawless smoothness. From a global viewpoint, Earth is considerably less uneven than depicted on our maps. This constitutes the initial insight into cosmic proportions. Entities that seem enormous at a particular observational level frequently turn almost imperceptible when the scale shifts. The Mariana Trench presents an exceptional engineering feat. For human exploration, Mount Everest stands as one of the most formidable environments our species has ever ascended. Nevertheless, when measured against the planet's complete dimensions, these two characteristics transform into minute imperfections on what would otherwise be a perfectly smooth sphere, yet the contraction doesn't cease at the planet's outer layer. Given that Earth is merely a single entity within a considerably vaster system, our world revolves around the Sun at an approximate separation of 150 million kilometers. Astronomers refer to this span as one astronomical unit, and this particular measure functions as a conventional benchmark for distances throughout the solar system. Nevertheless, once more, mere figures provide little utility without proper context. Envision traversing that expanse utilizing common velocities, such as a commercial aircraft constantly moving at 900 kilometers per hour, would necessitate over 19 years to arrive at the Sun. Even a missile journeying at the velocity of a potent rifle round, approximately 1,000 meters per second, would nonetheless demand more than 4 years to finish the voyage. Light itself moves at 300,000 kilometers per second, which is the maximum speed permissible under the principles of physics. Even photons take 8 minutes and 20 seconds to journey from the Sun to our planet. This implies that gazing skyward at the Sun reveals it to you as it appeared 8 minutes prior. Should the Sun abruptly disappear, Earth would keep on receiving solar illumination for upwards of 8 minutes before the heavens ultimately grew dark. However, separation constitutes merely half of the narrative. The sheer magnitude of the Sun itself is considerably more striking. Its diameter spans approximately 1.39 million kilometers, rendering it roughly 109 times broader than Earth. Were you to arrange Earths adjacent to one another across the Sun's expanse, 109 planets would be needed to extend from one boundary of the Sun to the opposite. The disparity in volume is even more pronounced. Approximately 1.3 million Earths could be contained within the Sun. Picture replicating our world, replicating each continent, every oceanic trench, every urban area, woodland, and peak, over a millionfold, and then enclosing them all within one solitary orb. Such is the magnitude disparity between Earth and its stellar parent. Nevertheless, the Sun isn't considered an exceptionally massive star. It falls into a prevalent classification referred to as G-type. Main sequence stars, which are abundant across galaxies throughout the cosmos. Numerous stars possess greater size and luminosity. Some boast diameters hundreds of times larger. Conversely, others are more diminutive, less luminous, and possess extended lifespans. What renders the sun significant to us is not its uncommonness, but its nearness, notwithstanding its typical standing among celestial bodies. The sun utterly governs the solar system. It comprises 99.86% of the aggregate mass of all celestial bodies revolving around it, including every planet and moon. While asteroids and comets collectively constitute merely a minuscule segment of the system's total mass. Earth, the complete setting for human society, signifies only an infinitesimal fraction of that remaining portion. Within the sun's central region, temperatures attain roughly 15 million degrees Celsius. In such circumstances, hydrogen atoms impact with sufficient kinetic energy to coalesce into helium via the process of nuclear fusion. This mechanism transforms a minute quantity of mass straight into energy in accordance with Einstein's renowned formula. Each second, the sun transmutes approximately 4 million tons of material into energy, which then emanates outwards through the cosmos as solar radiation. The sun has consistently maintained this energy output, heating the planets and fueling the intricate series of events that enable life to exist on Earth. This has occurred for approximately 4.6 billion years, and it's projected to persist for around an additional 5 billion years until its hydrogen reserves start to diminish. From our vantage point on Earth, the sun appears vast and potent. However, even this colossal star represents merely one luminous dot. It is one among countless billions dispersed throughout the Milky Way galaxy, and as soon as we expand our view to that scale, the reduction in size recommences. Comparing Earth to the sun reveals an already immense disparity in scale. A planet exceeding 12,000 kilometers in diameter becomes nearly negligible. When placed beside a star almost 1.4 million kilometers in width, over a million Earths could be accommodated within the sun's total volume. Furthermore, that solitary star comprises 99.86% of the entire mass within our solar system, encompassing every planet, moon, asteroid, and comet put together. These celestial bodies collectively represent only a minuscule portion of the sun's contents, yet the sun itself merely serves as the core of a far grander arrangement. Upon taking a broader view of the complete solar system, an astonishing fact emerges. The most prominent characteristic of our celestial vicinity isn't the planets themselves. Instead, it is the vast expanse of void that divides them. Earth revolves around the sun at an approximate mean distance of 150 million kilometers. This distance, termed 1 astronomical unit (AU) by astronomers, serves as the fundamental metric for charting the remainder of the solar system. As one starts charting the other planets with this measurement, the system rapidly extends outwards. Mars, the planet situated next after Earth, orbits the sun at approximately 1.5 astronomical units, which is around 228 million kilometers. Jupiter, the solar system's most massive planet, revolves considerably further out. Its orbit is approximately 5.2 astronomical units, equating to almost 778 million kilometers. Saturn comes next at roughly 9.5 astronomical units, with Uranus at about 19 astronomical units. Finally, Neptune, the primary planet furthest from the sun, revolves at almost 30 astronomical units, a distance equivalent to approximately 4.5 billion kilometers. The solar system, spanning from the sun to Neptune, already extends over a distance nearly 30 times larger than the separation between Earth and the sun. Even light, traveling at the maximum velocity permitted by physical laws, requires roughly 4 hours to journey from the sun to Neptune. Human-made technology progresses considerably slower. A spacecraft moving at approximately 60,000 kilometers per hour, a speed surpassing most probes launched by humankind, would require over 8 years to complete that identical voyage. If traveling at the constant speed of a commercial aircraft, without any interruptions, the expedition would span more than 5 centuries. These comparisons start to illuminate a foundational aspect of the solar system. The vast distances separating planets make them seem to vanish when compared to the immense void between them. A helpful method to picture this involves constructing a scaled-down model, reducing everything to a comprehensible size. Imagine the sun being compressed until it resembles a grapefruit, approximately 20 centimeters in diameter, positioned at a large building's entrance. On this scale, Earth would be a minuscule sand grain, situated roughly 22 meters from the grapefruit. Mars would appear as another sand grain, approximately 34 meters distant. Jupiter, the solar system's most massive planet, would be reduced to a small marble, situated around 115 meters from the entrance. Saturn would manifest as a different marble, roughly 210 meters further, whereas Uranus would be located nearly 430 meters from the Sun. Neptune would be discovered almost 700 meters away, nearly 3/4 of a kilometer from the grapefruit at the entrance. Within this representation, the whole solar system extends over multiple city blocks, though merely a few minuscule objects inhabit that vast expanse. Between them, there is solely vacant space. No atmosphere would fill the voids, no luminous dust clouds would delineate the planet's trajectories, and no clear markers would exist to direct you between worlds. Should you traverse from Earth's location to Jupiter's location in this model, the majority of your journey would involve crossing entirely barren terrain. This void represents the actual character of the solar system. The planets themselves are merely small islands dispersed throughout a colossal cosmic desert. The magnitude becomes even more remarkable when contemplating the actual distances covered by human spacecraft. In 1977, NASA deployed two automated probes named Voyager 1 and Voyager 2. Their mission was to investigate the outer planets. Following their respective planetary flybys, both probes proceeded to journey outward into the darkness past Neptune. Currently, Voyager 1 stands as the farthest human-constructed object ever created. After almost 5 decades of transit, it has attained a separation, exceeding 24 billion kilometers from Earth. Its radio transmission requires approximately 22 hours to traverse the immense expanse separating the probe from our world. Such a distance appears exceptional, and by human metrics, it undeniably is. Voyager 1 has journeyed further than any apparatus ever devised by humankind. Nevertheless, relative to the Sun's entire dominion, it has scarcely started to depart its immediate vicinity. Beyond Neptune exists an area known as the Kuiper Belt, a broad band of frozen celestial bodies, remnants from the solar system's initial development. This zone extends roughly 30 to 50 astronomical units from the Sun and encompasses innumerable icy vestiges of planetary formations such as Pluto and numerous other dwarf planets. However, even the Kuiper Belt does not signify the actual boundary of the solar system. Much further out lies a colossal and predominantly theoretical formation referred to as the Oort cloud. Rather than constituting a flat ring, similar to the Kuiper Belt, the Oort cloud might encircle the Sun within an immense spherical casing of frozen fragments. Certain projections indicate it could reach distances up to 100,000 astronomical units. To grasp the significance of this, recall that 1 astronomical unit, AU, represents the span separating Earth and the Sun. Extending outward, 100,000 such distances cover almost 1.6 light-years, implying the Sun's gravitational pull could reach nearly halfway to the closest star. Within this vast expanse, countless trillions of icy bodies float, remnants from the very beginning of our solar system's creation. Dating back over 4.6 billion years, the majority are too tiny and remote for direct observation, yet their existence is deduced. This inference comes from the long-period comets that sometimes journey inward towards the Sun. Seen from this viewpoint, the well-known planets Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune occupy merely a small central part of the Sun's domain. They orbit within the core area of a gravitational realm stretching for countless trillions of kilometers through space. Let's now revisit Voyager 1. Moving at approximately 61,000 kilometers per hour, the probe has spent almost 50 years consistently journeying away from the Sun, having traversed over 24 billion kilometers. Despite this, it remains far from the outermost edge of the Sun's gravitational reach. At its present velocity, Voyager 1 would need approximately 3 centuries merely to arrive at the Oort cloud's inner zones. Traversing that remote ring of frozen fragments entirely could span tens of millennia. Furthermore, even upon exiting the Oort cloud, Voyager would just be venturing into interstellar space. Proxima Centauri, the closest star system, is situated roughly 4.24 light-years distant. At Voyager's pace, arriving at that star would demand approximately 70,000 years, a duration significantly exceeding the entire recorded history of human civilization. The swiftest vessel ever launched by humanity is incapable of reaching the closest star within a time frame pertinent to the endurance of cultures, languages, or even species. This understanding underscores the solar system's genuine defining characteristic. It isn't the planets, nor the moons, nor the asteroids that primarily shape its structure. Rather, it is the immense void that separates all its internal components. Between Earth and Mars, tens of millions of kilometers of emptiness exist. Between Jupiter and Saturn, hundreds of millions of kilometers of vacant space stretch. Beyond Neptune, the separation between celestial bodies becomes so vast that the sun itself starts to appear as merely another star, dimly glowing in the blackness. From our vantage point on Earth, the solar system might seem densely packed with celestial bodies. In truth, it's a colossal area where matter is distributed remarkably sparsely, over distances that push the boundaries of human understanding. And when we withdraw even further, past the sun, beyond the most distant comet clouds, completely outside the solar system's confines, the scale once more amplifies, for the sun itself is just one star amidst hundreds of billions within the Milky Way galaxy. Upon positioning our solar system within that considerably vaster formation, all our previous measurements appear incredibly minuscule. This reduction persists. As soon as one moves past the solar system's periphery, every distance we've examined thus far undergoes an unusual transformation. The billions of kilometers separating planets, the decades spacecraft need to traverse these distances, and even the vast extent of the sun's gravitational pull, all these elements abruptly turn nearly negligible, given that the solar system itself constitutes merely a minuscule entity contained within a much grander framework. This more expansive formation is known as the Milky Way Galaxy. When viewed from Earth, away from urban illumination, it manifests as a dim, luminous strip extending across the nocturnal heavens. It resembles an ethereal river of light moving above us. Ancient cultures observed it well before the invention of telescopes and devised legends to account for its presence. The Greeks envisioned it as milk spilt across the celestial sphere, which is the origin of the name Milky Way. However, the true nature of that luminous streak is considerably more remarkable. The Milky Way constitutes a spiral galaxy, a spinning disk composed of stars, gas, and dust, spanning approximately 100,000 light-years. This figure is nearly inconceivable to picture, so it's beneficial to start by defining the unit. A light-year denotes the distance light covers over a single year. Traveling at a speed of 300,000 kilometers per second, light traverses approximately 9.46 trillion kilometers within a year, meaning that when astronomers state the Milky Way's width is roughly 100,000 light-years, they imply that a light beam originating from one side of the galaxy would take 100,000 years to arrive at the opposing boundary. This measurement represents the breadth of the formation housing our sun. Our solar system and every planet humanity has directly observed are situated within that colossal disk, which contains an estimated 200 billion to 400 billion stars. The precise count remains undetermined due to dense clouds of cosmic dust obstructing our perception of vast galactic areas. Infrared telescopes and comprehensive investigations have significantly refined our estimations, yet even with contemporary equipment, it continues to be challenging to enumerate each star within such an expansive system. What is certain is that the quantity is astonishing. If one tried to count every star in the Milky Way at a rate of 1 star per second, this endeavor would span approximately 6,000 to 12,000 years to finish. You would need to commence counting well before the pyramids were built, and persist far into the future before reaching the last star. Every one of these stars functions as a sun. Some considerably exceed the size of our own. Enormous blue supergiants can radiate with a luminosity tens of thousands of times greater than the sun's, while others are significantly smaller and less bright. Indeed, the most prevalent stars within the Milky Way are red dwarfs, small, dim stars that generate merely a minuscule portion of the sun's energy. A significant number of them are too faint to be seen without aid from Earth. Even though they constitute the most abundant stars in the galaxy, our Sun is positioned midway within this collection of stars. It shines more brightly than numerous other stars, yet it is far from being the biggest or most brilliant in a galaxy comprising hundreds of billions of celestial bodies. Our Sun holds no unique distinction. It represents a rather typical instance of a highly prevalent category. The placement of our solar system inside this immense galaxy is likewise notably unexceptional. The Sun revolves around the Milky Way's core, approximately 26,000 light-years away. We are not situated close to the densely packed central region, nor are we positioned at its outermost extreme. Rather, the solar system occupies a smaller spiral characteristic known as the Orion arm, situated between two more substantial spiral arms, specifically the Sagittarius arm and the Perseus arm. If the Milky Way were envisioned as an expansive metropolis, our solar system would be found in a suburban area, distant from the congested city center, but still comfortably contained within the primary urban framework. The Sun does not remain fixed within this cosmic setting. It traverses space with immense velocity, circling the galactic core at approximately 828,000 kilometers per hour. Such a speed appears colossal when measured by human metrics. However, the Milky Way is so vast that even at this pace, the Sun needs roughly 230 million years to finish one full revolution. This duration is occasionally termed by astronomers as a galactic year. The sheer magnitude of this figure itself generates one of the most profound changes in astronomical perspective. The previous occasion the Sun held its present location. Within the Milky Way, approximately 230 million years ago, Earth was an entirely distinct planet. Dinosaurs had just started to emerge, and the landmasses remained configured as the supercontinent Pangaea. Over the 4.6 billion years since the solar system's inception, the Sun has merely finished around 20 galactic revolutions. This signifies the total count of instances our star has traversed the Milky Way throughout its existence. From this viewpoint, the solar system appears nearly imperceptible. Should you be capable of journeying far beyond the galaxy and capturing an image of the Milky Way, the entirety of our solar system would not manifest as a discernible speck of light. The Sun itself would merge seamlessly with the innumerable stars encircling it, rendering it indistinguishable from billions of other celestial bodies dispersed throughout the galactic disk. To grasp the sheer minuteness of our solar system in comparison to the galaxy, envision reducing the Milky Way's size until it could be contained within a vast stadium. On that particular scale, the complete solar system, encompassing every planet, moon, asteroid, and comet, would be tinier than a single granule of sand. Positioned somewhere on the playing field, all that humanity has ever directly investigated would be enclosed within that solitary grain. The remainder of the stadium would be occupied by hundreds of billions of additional grains, each symbolizing a distinct star, potentially accompanied by its own planetary configurations. Nevertheless, even this comparison fails to entirely convey the galaxy's true magnitude, as stars themselves are set apart by immense expanses within the sector of the Milky Way where our Sun is located. The typical separation between adjacent stars measures approximately 4 to 5 light-years, which signifies that light requires multiple years to journey from one star to the next. Were we to reduce the Sun to the dimensions of a ping-pong ball, the closest star would then be another ping-pong ball, positioned hundreds of kilometers distant. Billions of these stars populate the galaxy, but the overwhelming majority of the volume between them is empty space. This arrangement, characterized by tiny objects separated by enormous distances, persists across every scale throughout the cosmos. Even the Milky Way's own structure demonstrates this equilibrium between matter and void. The galaxy's disk spans approximately 100,000 light-years, yet its thickness is merely about 1,000 light-years. In numerous regions, the bulk of observable matter is concentrated within that slender, rotating plane. Positioned both above and below the disk is the galactic halo, an expansive spherical area inhabited by ancient star clusters and primarily influenced by dark matter, an unseen substance that manifests solely through its gravitational effects. This dark matter halo could stretch for hundreds of thousands of light-years. past the visible disk, thereby creating a considerably larger structure that envelops the galaxy. From within the Milky Way, perceiving the galaxy in its entirety proves challenging. Extensive parts of our perspective are obscured by dust clouds, and our location inside the disk is akin to attempting to chart a forest while situated deep within its confines. To reconstruct its overall structure, astronomers depend on radio telescopes, infrared observations, and precise measurements of stellar movement. Notwithstanding these difficulties, one truth remains evident. The Milky Way is immense. It encompasses hundreds of billions of stars and vast gaseous nebulae where new stars originate. Also, the remnants of exploded stars, neutron stars, black holes, and immense areas of interstellar space where matter becomes extraordinarily sparse. Every star you have ever observed without optical aid belongs to this sole galaxy. Every constellation charted by ancient civilizations resides within its boundaries. Even the subtle, luminous band of the Milky Way stretching across the nocturnal sky is merely the aggregated light from billions of remote stars, densely concentrated along the galactic plane. However, here is the insight that once more begins to alter our perception of cosmic scale. The Milky Way is not solitary. For hundreds of years, astronomers held the belief that our galaxy constituted the entirety of the universe and that all visible objects in the night sky were part of a single colossal stellar system. It wasn't until the early 20th century that observations conclusively disproved this notion, specifically when astronomers started distinguishing individual stars within remote spiral nebulae. They made an astonishing discovery. Those faint luminous smudges dispersed across the sky were not gaseous clouds within our galaxy. Rather, they were galaxies in their own right. Complete stellar systems, comparable in magnitude to the Milky Way. And one of these is remarkably near, situated merely 2.5 million light-years distant. An additional galaxy drifts within the darkness of intergalactic space. It possesses sufficient size to be discernible to the unaided eye from Earth, provided the skies are dark. The galaxy known as Andromeda, when contrasted with our own Milky Way, which lies directly beside it, makes even our home galaxy appear smaller than previously. After astronomers understood that the Milky Way did not encompass the whole universe, the true scope of reality rapidly broadened. For many centuries, people had observed dim, luminous areas in the heavens, features that seemed indistinct even when viewed with primitive telescopes, and presumed these were gaseous clouds within our galaxy. They received the name nebulae, a term signifying cloud. However, by the early 1900s, meticulous observations started to uncover something considerably more astonishing. As astronomers directed progressively stronger telescopes toward a specific nebula, located within the Andromeda constellation, they observed an unforeseen phenomenon. Rather than presenting itself as a uniform cloud, the entity commenced to differentiate into distinct points of illumination. These points were stars, and upon astronomers identifying a unique category of pulsating stars, known as Cepheid variables inside that nebula, they at last possessed the necessary instrument to gauge its remoteness. Cepheid stars fluctuate in brightness at regular periods, and the duration of this cycle indicates the star's actual luminosity. By contrasting the star's inherent brilliance with its apparent faintness when viewed from Earth, astronomers are able to compute its precise distance. When this method of measurement was utilized for the stars within the Andromeda Nebula, the outcome proved astonishing. The separation was excessively vast, preventing the object from being part of the Milky Way. The dim mark in the heavens was not an intragalactic cloud. It constituted a complete galaxy in its own right. Currently, we identify that entity as the Andromeda Galaxy, positioned approximately 2.5 million light-years distant from Earth. Even traveling at light speed, the voyage from that galaxy to ours requires 2.5 million years. The photons arriving at your eyes when you observe Andromeda this evening commence their travel well before the advent of modern humanity. Notwithstanding that immense separation, Andromeda remains the farthest celestial body discernible without optical aid. In unpolluted night skies, it manifests as a dim, stretched-out area of illumination within the constellation bearing its name. Without the aid of telescopes, it seems unremarkable, merely a gentle luminescence. Yet, that radiance conceals something colossal. The Andromeda Galaxy extends approximately 220,000 light-years through space, rendering its diameter over double that of the Milky Way's observable disk. Within that colossal formation, roughly 1 trillion stars are situated. This figure by itself is challenging to comprehend. If the Milky Way encompasses between 200 and 400 billion stars, then Andromeda could potentially contain multiple times the number of suns found in our galaxy. Each of these stars functions as a nuclear furnace, similar to our sun. Many probably harbor their own planets, and some might possess planetary systems considerably more intricate than our own. Nonetheless, the collective light from that trillion-star system arrives at us merely as a dim, indistinct image when astronomers examine Andromeda. When viewed through potent telescopes, this galaxy displays a configuration largely resembling our own. It's a spiral type featuring extensive, curving arms composed of stars, gas, and dust, all revolving around a compact core. Andromeda's disk teems with luminous groupings of nascent stars, radiant nebulae, sites of stellar birth, and obscure dust lanes that extend throughout its spiral arms. At the galaxy's heart resides a supermassive black hole, estimated to be about 100 million times the Sun's mass. In contrast, the black hole situated at the Milky Way's core, dubbed Sagittarius A, holds approximately 4 million solar masses. Consequently, Andromeda's core black hole possesses roughly 25 times greater mass, compared to the one that stabilizes our own galaxy. Andromeda additionally features a substantial number of globular clusters, compact spherical aggregations of ancient stars, which revolve around its galactic nucleus. Whereas the Milky Way has around 150 identified globular clusters, Andromeda accommodates several hundred, potentially exceeding 400. Each of these clusters can encompass hundreds of thousands of stars, densely concentrated within areas merely a few dozen light-years in diameter. However, Andromeda is more than just an enlarged iteration of the Milky Way. It also stands as the primary constituent of a modest galactic collective inhabiting our cosmic vicinity. Within the assemblage termed the Local Group, the Milky Way and Andromeda represent the two most massive galaxies. This gravitationally bound family comprises over 80 identified galaxies, although the majority are diminutive dwarf galaxies, each holding just a few billion stars or less. The Local Group extends approximately 10 million light-years, and almost all its constituents revolve around either the Milky Way or Andromeda. Among these accompanying bodies are galaxies like the Triangulum Galaxy, housing approximately 40 billion stars, alongside numerous smaller dwarf galaxies gradually being disrupted by tidal gravitational forces. Both the Milky Way and Andromeda possess their individual collections of satellite galaxies. The Milky Way is orbited by entities such as the Large and Small Magellanic Clouds, observable from the southern hemisphere, as dim luminous areas close to our galaxy's periphery. Andromeda, too, has its own satellites, among them M32 and M1110, a pair of small elliptical galaxies that circle near its disk. In numerous aspects, the Local Group mirrors a compact cosmic vicinity. Two substantial galaxies exert dominance over the area, while lesser galaxies meander around them. Much like satellites, sometimes undergoing disruption and assimilation over extended periods. Yet, the most striking characteristic of the interaction between the Milky Way and Andromeda is not merely their closeness, but rather their movement. In contrast to the majority of remote galaxies, which seem to recede from us due to cosmic expansion, the Andromeda Galaxy is in fact approaching the Milky Way. Astronomers ascertain this by analyzing the Doppler shift in Andromeda's emitted light. When an entity advances towards an observer, its light's wavelengths undergo compression, causing a shift towards the blue portion of the spectrum. This occurrence is termed a blue shift, and Andromeda's light distinctly exhibits this phenomenon. This indicates our galaxy is moving closer to us. Observations show the Milky Way and Andromeda are converging at approximately 110 kilometers per second. This amounts to roughly 400,000 kilometers per hour. While that seems incredibly rapid, the immense separation between these galaxies means their convergence will span billions of years until completion. Contemporary simulations propose that the pair of galaxies will undergo their initial close approach in approximately 4 to 5 billion years. Upon its occurrence, this event will not mirror a standard impact. Despite housing hundreds of billions of stars, galaxies are largely composed of vacant space. Stellar distances are so immense that direct impacts between stars are exceedingly rare. Rather, the interaction will manifest through gravitational pull as the galaxies traverse one another. The galaxy's spiral arms will elongate and contort. Immense flows of stars will be drawn out into lengthy tidal tails. Gaseous clouds will impact and compact, sparking surges of vigorous starbirth. Within both galaxies, throughout several billion years, the two galaxies will slowly combine to form a singular, more massive system. This future galaxy is sometimes dubbed Milky Amida or Milkdromeda by astronomers. When the amalgamation concludes, the refined, helical structures of both galaxies will probably vanish, superseded by a colossal elliptical galaxy potentially holding 2 trillion stars. Should the Sun still be present then, it will be approaching its final stages. Our solar system will likely endure the merger. However, its trajectory within the galaxy could alter significantly. Some models indicate the Sun might be ejected further from the galaxy's nucleus, potentially into the enlarged halo of the fused galaxy. Viewed from Earth, the nocturnal firmament would slowly evolve over millions of years. Andromeda would expand in size and intensify in brightness, ultimately occupying a significant portion of the sky as the galaxies drew nearer. Yet, even this spectacular cosmic occurrence progresses slowly when measured against human timescales. The amalgamation of galaxies spans hundreds of millions to billions of years. No human could ever witness the complete process, and yet the most remarkable understanding awaits. Since even though Andromeda appears incredibly remote, it is still counted among the closest major galaxies to our own. Outside the local group reside millions of other galaxies, each separated by even more immense distances. Upon commencing the measurement of these distances, the universe's scope expands anew. When we arrive at the scale of galaxies, the magnitudes have already exceeded ordinary comprehension. The Milky Way stretches roughly 100,000 light-years wide and houses hundreds of billions of stars. The Andromeda Galaxy, our closest substantial neighbor, spans an even greater expanse and could contain almost 1 trillion suns. Nevertheless, the most significant characteristic of the bond between these two immense galaxies isn't their magnitude. It's the expanse separating them. The Milky Way and Andromeda are divided by roughly 2.5 million light-years of cosmic expanse. Such a vast distance means that even light, the universe's fastest phenomenon, takes 2.5 million years. To grasp the implications of intergalactic travel, it's beneficial to convert such figures into a more concrete representation. A single light-year measures approximately 9.46 trillion kilometers. When this is multiplied by 2.5 million, the distance separating the Milky Way and Andromeda totals around 24 quintillion kilometers. Expressing this figure numerically necessitates 19 digits. Such immense quantities soon cease to function as typical distances. They no longer depict voyages or specific places. Rather than being perceived in the manner our minds typically envision them, these distances start to signify whole epochs. Consider the light from Andromeda that arrives here tonight. Those light particles departed their galaxy 2.5 million years prior. Back then, Earth presented a vastly different appearance, with early human forebears just starting to ambulate bipedally. Throughout the African continent, the initial members of the Homo genus had not yet emerged. Stone implements, urban centers, farming practices, and codified communication were all part of a future those photons had not yet encountered. During the period that light traversed intergalactic expanses, whole segments of our planet's past transpired. Glacial periods occurred and receded, species developed and disappeared, and human societies arose, constructing urban areas and pioneering scientific inquiry. Ultimately, humanity devised instruments, specifically telescopes, able to discern the subtle luminescence that had journeyed towards us from a time predating our own species. Put differently, observing the Andromeda Galaxy means you are not witnessing its current state, but rather its appearance 2.5 million years ago. The immense separation between galaxies is such that it transforms the cosmos into a temporal device. Each telescopic viewing simultaneously offers a retrospective look into universal history. However, the sheer magnitude of this distance itself uncovers an even deeper truth. The region separating the Milky Way and Andromeda is nearly entirely devoid of matter. The void between galaxies does not contain nebulae, asteroid belts, or isolated planets meandering through the gloom. On average, the material density within this expanse is approximately 1 atom per cubic meter. To provide a reference, the atmospheric air you are currently inhaling holds roughly 10^25 molecules per cubic meter. The expanse between galaxies represents one of the cosmos's most flawless natural vacuums. Consequently, if one were hypothetically able to position themselves centrally within the vast chasm, separating the Milky Way and Andromeda, they would perceive themselves enveloped by nearly absolute emptiness. There would be no proximate stars, no celestial bodies, and no discernible formations. Even the galaxies themselves would manifest as remote islands of dim illumination suspended within an immense quiet void. The true extent of this desolation becomes more apparent when we construct an alternative conceptual framework, envision reducing the entirety of the Milky Way galaxy until it matches the dimensions of a solitary rice grain positioned at the midpoint of a sports field. This single grain of rice symbolizes a galaxy comprising hundreds of billions of stars. At this reduced proportion, the Andromeda Galaxy would be represented by another grain of rice, situated approximately half a kilometer distant. Everything in between them, the entirety of the intergalactic void, would be an unoccupied field. This comparison highlights an extraordinary aspect of the cosmos. Despite galaxies being immense formations, the vast expanses between them are so immense that these galaxies spend the majority of their lifespan entirely cut off from each other, much like remote islands floating in an infinite cosmic sea. Our galaxy, too, is merely one such island among countless others. Experts now calculate that the visible universe holds hundreds of billions of galaxies, with certain studies indicating the total could surpass 2 trillion, when less luminous dwarf galaxies are factored in. Each of these galaxies houses anywhere from millions to trillions of stars. If one combines these figures, the resulting total is nearly inconceivable. The visible cosmos might possess a greater number of stars than the total grains of sand found on every beach across Earth. However, notwithstanding this astonishing profusion, the universe largely remains vacant. Between galaxies, vast areas extend where matter is exceedingly scarce. These areas constitute a component of a formation referred to as the cosmic web. Galaxies are not randomly dispersed throughout space. Rather, they congregate along extended threads of matter, which extend throughout the cosmos, akin to strands. At the points where these filaments intersect, one finds galaxy clusters, enormous gravitational assemblies comprising hundreds or even thousands of galaxies, held together. Between these filaments are immense voids, which are spatial zones containing extremely few, if any, galaxies. Some of these empty regions span hundreds of millions of light years. Should one traverse the universe at its grandest dimensions, galaxies would appear organized into expansive networks, encircling colossal vacant areas. This arrangement would bear a resemblance to a three-dimensional spiderweb composed of galaxies and dark matter. And within this vast cosmic network, the Milky Way and Andromeda inhabit merely a tiny segment. The local group, which is the gravitationally bound region encompassing both galaxies, extends approximately 10 million light-years. Inside that particular area, the Milky Way and Andromeda exert primary control over the group's mass and configuration. All other entities, including dozens of smaller dwarf galaxies, are subject to their collective gravitational pull. However, the local group itself represents just a minor part of a considerably grander formation. Beyond it resides the Virgo supercluster, an enormous aggregation of galaxy groups and clusters, spanning over 100 million light-years across space. Even this particular structure constitutes only a portion of an even vaster entity, an expansive domain that astronomers have named Laniakea, a supercluster complex that stretches approximately 500 million light-years. The further scientists peer into the cosmos, the more these colossal formations become apparent. Consistently, at each scale, the identical arrangement recurs. Galaxies gather in clusters, separated by such immense distances that even light itself needs millions of years to traverse them. Nevertheless, one truth persists. Despite the immense quantity of galaxies throughout the universe, the overwhelming portion of space is devoid of matter. This void characterizes the fundamental design of the cosmos. Stars are separated by light years, galaxies by millions of light years, and between them extends a profound stillness, which utterly overshadows anything encountered on Earth. Yet, even across this incomprehensible expanse, gravity remains active. The Milky Way and Andromeda are not moving away from each other. Unlike the majority of galaxies in the expanding cosmos, their reciprocal gravitational pull is gradually drawing them closer together at this very instant. The Andromeda Galaxy is currently approaching us at a speed of roughly 110 kilometers per second. This movement has been occurring for billions of years and is set to persist for several more billion years. This process will persist, and eventually the two galaxies are destined to converge. Yet that encounter, along with what it unveils regarding the universe's spatial boundaries, constitutes the subsequent stage in this journey through scale. At each progression, the same pattern recurs. Something once perceived as immense suddenly appears diminutive when viewed from a higher perspective. Nevertheless, when we ultimately face the immense distances separating galaxies, a different outcome emerges. Instead of merely another upward step in scale, we encounter a frontier, one that exposes the limitations of travel technology and even human imagination. The expanse separating the Milky Way and the Andromeda Galaxy spans approximately 2.5 million light-years. Light traveling at 300,000 kilometers per second would require 2.5 million years to traverse this expanse. That figure by itself already strains the boundaries of human comprehension, but it becomes even more remarkable when contrasted with the capabilities of the machines we have actually constructed. Consider the swiftest spacecraft ever launched into deep space by humanity. The Voyager 1 probe, deployed in 1977, is presently journeying at approximately 61,000 kilometers per hour relative to the Sun. At this velocity, it has traversed over 24 billion kilometers from Earth in nearly half a century. By human standards, this represents an extraordinary achievement in engineering and exploration. However, when we contrast that speed with the distances between galaxies, the outcome is astonishing. At Voyager's current velocity, reaching the Andromeda Galaxy would necessitate approximately 40 billion years. That duration is roughly 3 times the current age of the universe. Stated differently, if Voyager 1 had been launched at the precise moment the universe itself began, almost 13.8 billion years ago, it still would not have arrived at Andromeda by today. It would still have tens of billions of years of travel remaining. This illustrates the immense scale of intergalactic space. Even if we envision spacecraft far swifter than anything currently in flight, the figures remain formidable. Let's hypothesize that a future civilization develops technology capable of accelerating a spacecraft to 10% of the speed of light, roughly 30,000 kilometers per second. At that velocity, the voyage to Andromeda would still consume approximately 25 million years. 25 million years ago, on Earth, the planet was inhabited by the early ancestors of modern apes. The continents featured different coastlines, climates varied, and the entire lineage that eventually gave rise to human civilization had only just begun to emerge. A spacecraft traveling at 1/10 the speed of light would necessitate a journey longer than the entire evolutionary history of our species. Even if we envision pushing technology even further, approaching half the speed of light, the expedition would still demand approximately 5 million years. This duration approximates the period that has elapsed since humanity's earliest forebears commenced bipedal movement across the African savanna. Galactic distances do not function like those separating cities or even planets. They fall into a completely distinct scale category, and this understanding compels us to acknowledge a significant truth regarding the cosmos's structure. The principles of physics dictate maximum speeds for matter. No object possessing mass is capable of exceeding the speed of light, and nearing that threshold necessitates vast quantities of energy, propelling even a moderately sized spacecraft to a considerable percentage of light's velocity would necessitate energy generation akin to stellar production. Sustaining such a speed, safeguarding a vessel from cosmic radiation, and ensuring a secure deceleration upon arrival would introduce difficulties vastly exceeding humanity's present problem-solving capabilities. However, even if such engineering hurdles were surmounted, the temporal challenge would persist. Journeys between galaxies are quantified not in years or centuries, but rather in millions of years. No living entity endures sufficiently long to undertake such voyages. Even societies themselves seldom persist beyond a few millennia, prior to evolving or vanishing. A voyage spanning millions of years would necessitate a space vessel capable of supporting more than just solitary voyagers, but complete ecosystems and entire societies throughout geological epochs. Certain researchers have put forward notions like generation ships, massive craft transporting self-sufficient populations that procreate over numerous generations during interstellar travel. In principle, a vessel of this kind might enable the progeny of the initial crew to arrive at remote destinations, yet extending this concept to intergalactic voyages swiftly exposes its inherent challenges. A voyage extending for millions of years would necessitate a civilization's ability to preserve consistent technology, societal stability, genetic variety, and environmental equilibrium, for a duration exceeding the survival span of most terrestrial species. The earliest documented human societies have persisted for merely a few millennia. Even the entirety of the Homo sapiens species has existed for approximately 300,000 years. An expedition enduring 25 million years would encompass a period exceeding 80 times the complete history of our kind. By that stage, the expedition would cease to resemble exploration in any discernible manner. It would transform into something akin to the gradual movement of life itself across vast cosmic expanses. Nevertheless, the cosmos abounds with distances precisely of this magnitude, extending beyond the local group of galaxies. Reside clusters and superclusters extending over tens and hundreds of millions of light-years. Among the most colossal formations within the discernible cosmos encompass billions of light-years. The further scientists peer into space, the more evident these colossal scales become. However, herein lies the paradox. Despite our inability to journey to these remote galaxies within any practical time frame, we are still able to examine them using contemporary telescopes. Astronomers are able to gauge the movement of galaxies located billions of light-years distant. Through examining the light these galaxies give off, researchers can ascertain their makeup, their speed, and even the activities taking place within their stars. The cosmos, while physically immense, is also readily observable. Information is conveyed across immeasurable distances by the light reaching us from far-off galaxies, photons that commence their voyages millions or billions of years prior, ultimately arrive at our telescopes, disclosing the universe's appearance long before Earth's formation. Thus, astronomy transforms into a type of exploration, which doesn't necessitate physical journeys. While we are unable to traverse the vast space separating galaxies, we can quantify it and examine the light that spans it. We are capable of rebuilding the structure and past of celestial bodies so remote that no space vehicle could ever get to them, and this brings about a concluding change in viewpoint. Gazing at the night sky, we perceive merely a minuscule portion of the cosmos. The majority of galaxies are situated at such immense distances that their illumination is visible solely via potent telescopes. Even so, every dim speck within a profound astronomical photograph could signify a complete galaxy teeming with billions of stars. The cosmos extends far beyond typical understanding. Nevertheless, it's extraordinary that a species inhabiting a minor rocky world circling a rather unremarkable star has succeeded in quantifying that immensity from Earth's surface. Employing mathematics, telescopes, and inquisitiveness, we have charted the separations between stars,